So good morning. My name is Pamela Gertzen, and I'm the Executive Director of the Smart Sustainable Resilient Infrastructure Association. We shorten that to SRIA just to help everyone out. I'm really happy that you were all able to join us for today's webinar that is being hosted in partnership with Intuitive. Intuitive is a full service consulting engineering group with a really strong sustainability focus. So we're glad to have them as a SRIA member and to be showcasing them this month as part of our Member of the Month feature. You can actually read a full feature on Intuitive on our website, which I'll actually link that particular article in the chat once we get started here. So at SRIA, our mission is to accelerate the adoption of innovative low carbon solutions for buildings in order to revolutionize the design, construction, and operations of buildings to reach the very important target of a zero carbon built environment by 2050. So we activate that mission and vision by providing support and growth opportunities for all companies in the industry in the form of demonstration project funding, business growth services, and sharing the latest expertise in innovative low carbon building technologies, products, and practices. So part of that is even having sessions like today. Today we were filing this one under what we call peer learning sessions. So you get to learn from your fellow engineers, building envelope specialists, and passive house certified designers. So really excited to have both Timothy and Nikolay here today to speak to us about a couple interesting case studies that they've worked on that are focused on kind of applying how they've applied passive house design and high performance building envelope to some multifamily housing with kind of a focus on affordability, which is remains a really important part of the conversation. So with that, I will actually pass it off to, I believe Timothy's going to get started.
Thanks, Pam, for the introductions. That's great. I don't think we need to introduce ourselves, actually. So I will go ahead and take the screen here. All right. And if I can get a thumbs up, or if everybody can let me know when you can see it. Great. Yep. Okay. So yeah, really quick. Definitely happy to be here, both Nikolay and I. What we've found would be an interesting topic to share with you is some of our work that's ongoing both in design phases and in construction stages. And in particular, our passive house projects, which are in the sort of multifamily mid-rise to high-rise realm. And in particular, these two projects have some interesting backgrounds. One is on the design side, this is the McLeod Manor in Vancouver, which is a mid-rise on the left, which originally was conceived as just a standard code compliant building, but transitioned to a passive house certified target construction. So I'll be walking through that project. And then Nikolay has also been actively, very consistently involved with the Sobel Tower in Hamilton, Ontario, where there's a high-rise retrofit achieving the ENERFIT standard through passive house certification.
Yeah, just a small comment on that. The Sobel Tower is an affordable housing project for the city of Hamilton, just as a background.
And the McLeod Manor is also a affordable housing project. So I think there's some interesting challenges when that is a criteria. Real quickly here, Intuitive, where we span about 7 offices. I'm located in the Vancouver office. I have a background in architecture and engineering. Got my passive house certification last year, actually, and then been actively involved in the facade industry and envelope industry for about the last 8 years or so. So, Nikolay, do you want to
Yeah,
Hello.
all right on. Likewise, I have an architectural background specializing in building science, got my certified passive house designation in 2019. And my role at Intuitive, I do a lot of contract administration and design assistant services for the client and the contractor. So I worked on the Sobel Tower from both the design and oversaw a lot of most of the contract administration stuff. And we'll be talking about the challenges we face during construction with the trades to make sure they understand the principles of passive construction. All right.
And then just some context on what we do as well, outside of the passive house realm. We're both specialized in building envelope, but our team members also consist of advanced performance analytics, sustainability, restoration, retrofits, structural engineering, fire engineering, and mass timber engineering, construction engineering, and bridge engineering. Those are some of the primary services that we offer as a firm. And what's I think really great about our environment so far is that we've been able to leverage those with passive house and sustainability as our goals with every project that we undertake. So I think today everybody's here to sort of learn about some of the principles of passive house if you're unfamiliar with them. We wanted to talk briefly about certification process and advocacy, as well as I'll be focusing primarily on some of the design methodologies. Nikolay will be looking at the construction methodologies with the case studies. And we've also like to sort of bring in some discussion about low carbon and net zero pairing with the passive house principles.
All right. So let's jump into it. The first passive house recorded and constructed to the current standard known today is the 1991 Darmstadt passive house. This came out to be as a research project between the university and the contractors, where each step of the way, the construction and design process was documented in great detail. And I want to spend a minute looking at this image here. The biggest factor in passive house is the heating that you receive through the sun, is solar heat gain. So you can see on this image, there are no windows on the right-hand side of this building, because the design team and the design of this building focuses on managing the amount of sun coming in during the various seasons of the year. And since this construction, this house has been tested throughout the last 30 years or so, and it's been proven quantitatively that it still performs the same way it did in 1991, and it achieved all the passive house targets when it was first constructed. Right. This is a great image showing the 5 biggest principles of passive house. We have everything from super insulated walls, airtight construction, which is one of the testing requirements, thermal fridge redesign, so no penetrations or minimize penetration as much as possible. There's strict calculation rules that we have to follow and avoid, high performance windows to manage solar heat gain, and ventilation and recovery system. And we'll talk about that a bit more further on. You want to handle this one, Tim?
Yes. So some of the benefits that, beyond energy efficiency that we've also sort of found through experiences, through case studies and precedents, is that passive house has, not only with the principles, is also trying to achieve year-round stable, healthy indoor air quality and temperature. I think a lot of people talk about passive house as being a sort of an airtight assembly, and it's really in terms of sort of consolidating that healthy environment within a living space. On top of the super insulated approach, there's the factor of quiet and comfortable sort of acoustic performance throughout the seasons. Depending on where you're located, the super insulated keeps the elements out, keeps the acoustics and vibrations out of the sort of residential space. The other thing is that we often see a substantial reduction in energy use and operating costs because we are relying on passive strategies and minimizing the mechanical and active systems. We're able to sort of really let our buildings work with themselves through our own maintenance or our own sort of manipulations with the envelope. That being said, those interfaces have to be simple to use and have to be durable. And most precedents have also shown that that is the case. And I think it'll just a last point there, priceless peace of mind. With those comfort criteria in mind, that's how we're hoping to provide living spaces. As we move into just the understanding of the Passive House Institute and the Passive House bodies for certification, I wanted to give just a brief overview of the programs that are out there from Passive House Institute. They have the regular classic certification. They have expanded that though to encompass energy source creation and generation on site, so that you're starting to see sort of levels of Passive House compliance, that is the plus and the premium, and the premium actually starts to discuss about how we're getting our source energy and actually providing a rating and an understanding of that source energy. We also have Passive House for existing buildings, and I think Nikolay's case study number 2 will be the Sobel Tower would be a great example of how retrofit is entirely possible with Passive House. Outside of the building certification, we also have in Passive House component certification. And I think that that's good to understand from an outside party, from a manufacturer standpoint, contractor standpoint, that there are components and products out there that are Passive House certified, whether it's the glazing systems or the insulated envelope systems, prefabricated envelope systems. Those can become pre-certified and actually make the certification process easier, as well as sort of verify and validates a lot of the performance of these assemblies that we install in the field. And then we also have professional certification, where professionals are pursuing that sort of knowledge. When we talk about the 5 principles, those 5 principles are actually metrics or calculable, can be calculated. And these metrics in particular are below in this table. So primarily the heating demand and heating load is the key metric for determining Passive House compliance, and it often becomes your leveling element. But then we also calculate cooling. We also keep in mind air tightness, and we review the primary energy renewable. As sort of Passive House has expanded as well, there have been more metrics or criterion that have been developed for health and comfort. A large topic at the moment is frequency of overheating. And so there is a metric to keep that under a comfortable level. There is a frequency of excessively high humidity. So those are metrics that are built into the Passive House planning package software. There's also minimum thermal protection for interior surface temperatures, mainly for that sort of comfort level of having cold surfaces on the interior. And then a general criterion of providing occupant satisfaction, which is determined by creating occupant control mechanisms, passive mechanisms that can level or can balance out the comfort.
Yeah, just to touch one more point from Tim's slide previously regarding the minimal thermal protection. One of the Passive House requirements is that at no point should the interior surface of the wall or window, the difference between outside temperature, inside temperature, should be within a 5 degrees Celsius difference. So if it drops less than 5 degrees Celsius, we're not really achieving the Passive House effect. All right, let's go to the next slide. There is a rigorous design considerations for Passive House. So when we do in the design phase, we do energy modeling, and where we make where we input our building envelope performance into this PHPP Excel energy model, and we identify the different wall assemblies, the different windows components. We measure the chi values for a linear thermal transmittance. That all gets measured out, where we need to maintain an annual space heating demand of less than 15 kilowatt hours per meter squared per year, I believe. Correct, yes. That is a pretty high target, especially with the colder climates here. Therefore, if we have windows, or we can't just plop windows all over the facade, we have to think critically about this. Where do we place them to get the best results for the winter, to get as much heat in the building as possible? And in the summer, how do we shade that with the sun's rotation to reduce the amount of heat loads coming in? So we want to prevent any cooling in the summer through these passive means of opening up the windows for ventilation or air circulation. So that's during the design phase with the PHPP model. Let's go back one second. I just want to mention the air testing. After the building has been constructed, there is a physical test where we test the whole building for air tightness. We pressurize it, and we measure the air leakage rate. And this is a strict requirement where we need to meet 0.6 air changes per hour at 50 pascals. That's a pretty strong benchmark, hard to achieve in most cases. For reference, the Sobel Tower, we did a base building test and we got a value of 8 air changes per hour. We recently did, or half a year ago, we did our final air test with all the completed envelope, and we actually got to 0.2 air changes per hour. Now, take that with a grain of salt. This is a really tall building, so the calculations are a bit skewed because of the volume of interior space. We had some openings in the service doors, for example, which would have impacted a residential, like a 2-story residential house, a lot more significantly than it does a 18-story tower. But nevertheless, we were really happy with that outcome. Next slide. Yeah, 15 kilowatt hours per. We kind of just talked about that. It's really important to control how much heating energy is required during the winter months, and we rely on solar heat gains for that. Next slide. This slide is a good comparison between the passive house requirements and conventional building code requirements. So this is just a visual graphic showing what level of improvement we're getting with passive house. So we're talking here almost 90% reduction in space heating and virtually no energy requirements for cooling, again, because we're relying on passive principles. Next slide. Reference targets. So how passive house works versus LEED, for example, is we have design criteria which we need to meet from the start. So we put a limit onto how much energy use we can have, and whereas another certification process for LEED, for example, is we have a drop-down list, for example, of what things we can throw into this building to make it sustainable. And we try to get as much of that as we can. Passive house, like from the start, this is the design performance that you need to meet, and you need to meet it. Anything worse than that does not meet our requirements. Next slide. Talking about the net zero approach, a net zero building is a building that produces as much energy as it consumes. That being said, like we can put solar panels on our building to give us some extra energy, ground source heat pump, for example, to reduce the energy load. But it's a lot more challenging to do with a building code design building, for example, because our energy use or our heating demand is so high. Whereas if we go with passive house, we reduce our energy needs by 90%. Therefore, we don't have to go crazy over the top with sustainable, like solar panels, for example. It's a lot more achievable and doable with this approach. Next slide.
Yeah, so I can jump here. What we wanted to also, given that we know the criteria, the performance metrics, who gets involved and how are they involved in this process? Typically, we do engage a passive house consultant who is part of the design team. And then on top of that, there is a passive house certifier that guides you through the process of certification through the legal body. But then quite often we recommend that also the general contractor engages with passive house tradespersons as their install team, or has dedicated air barrier specialists on their staff in order to streamline the process. Back to certification understandings is how frequently do we sort of engage with those bodies throughout the design process. And you'll see in some of the projects that we talk about that happens at various milestones, but it is a very active process and an active communication. As we kind of wrap up the sort of summary of Passive House, the one thing I wanted to leave you with was with a graphic that was created by one of our peers at RDH. Interesting graphic of how Passive House relates to its sort of adjacent and neighboring standards, and through sort of a timeline approach, how it is related to our zero carbon pursuits and our net zero pursuits, as well as various codes internationally. I think this jumps us right into our case studies. So I will start off with the McLeod Manor. It is a 6-story senior living redevelopment housing project in Vancouver. The development team is Brightside Community Homes Foundation. Colliers Canada is the project manager, and Integra Architecture is the architect of record. So an interesting project because the impetus for the project is actually to replace the existing McLeod Manor building, which is a 3-story residential senior living complex, and actually grow that sort of unit capacity and enhance the building as well. So as you can see here is the existing facade as well as its location. In Google Maps, you can notice that it is actually directly adjacent to one of the larger thoroughfares that is currently undergoing a lot of development. So this will tie into sort of the design impetus, is that there are a lot of neighboring buildings that are increasing in height. And so this project is responding to that increase in density as well. Key project statistics before I get into the Passive House details. Site area of 2,150 square meters, gross floor area of 6,030 square meters, FSR of 2.68. The existing McLeod Manor had about 46 units. We're increasing that to 100. So that is almost a double of the existing conditions, and it will be a mix of various studios, 1-bedroom, 2-bedroom, 3 bedrooms. There's a decent amount of glazing area in order to allow for a lot of daylight and natural ventilation opportunities, and we'll see that as I go through the elevations. So as I mentioned, the project was kind of interesting. For one of the features is that originally when it was developed prior or after rezoning, actually, we were actually pursuing a typical BC step code target, step code 3. But as more discussions revolved with the ownership and the development team, it was determined that Passive House would be a great sort of pursuit for this project and application for this project. What that did, though, is that really triggered some challenges because the building being conceived originally with a BC step code in mind didn't have the same sort of criteria for performance metrics. And so right off the bat, there was a intense sort of restudy of the project, restudy of the openings, the massing, and the configurations on all the elevations in order to make sure that performance or that could meet the Passive House criteria would be achievable. So as you can see, these are the sort of the early renderings, and actually you'll notice a lot of these articulations have been adjusted. A lot of different ins and outs and balcony protrusions and projections have been adjusted accordingly. And the reason for a lot of those balcony protrusions and adjustments is actually driven by sort of the city requirements. There's been a desire to avoid, I think often when people visualize Passive House, they visualize a very monolithic face or mass. And in this case, there was a high impetus to provide a less block-like massing in the neighborhood because of the surrounding context. So articulation and setbacks were actually very crucial to the ownership team. So some of these I've actually discussed. Another aspect or challenge was the 100% affordable housing budget constraints. So that also drives a lot of passive house criteria. A lot of times we're using passive house certified components, which do have a higher cost input. And at that point, we do need to keep that in mind. So we actually have engaged the general contractor quite early on in those discussions and provided many cost estimation through that process. One thing that we've touched upon was overheating, and which is becoming more and more relevant and very sort of intricate in terms of how we determine, how we validate overheating. In particular, for this project, we engaged with TransSolar. They provided some preliminary, based on our project conditions, evaluations of worst case scenarios. And as you can see to the charts on the right, the Southwest is demonstrated on the top right. Most of those heating days actually fall above the comfort range that's allowable. What that does is it really lets us narrow in on areas of the facade, areas of the program, and determine how we can mitigate that. So when we talk about mitigation strategies or simplifications or improvements of the envelope performance, one of the first things we did, as I mentioned, was to target the massing. You can see that a lot of these elements that are articulations or demonstrations of the facade were not as efficient and had a negative impact on our envelope performance. So early studies and early modeling allowed us to sort of narrow in on these and provide, either eliminate or simplify or modify to highlight the ones that were crucial to the project goals and objectives. In blue are some areas also to consider, is that there are large volumes that are actually either not part of the thermal envelope or outside of the thermal envelope. And in some cases, they would also be large setbacks, creating soffit returns and cantilevers, which again are not efficient in terms of the envelope. In orange, you can see some of the highlighted windows. So we focused particularly after the study on the overheating, that we wanted to be able to provide opportunities for passive cooling. And some of those passive cooling strategies are actually simply enlarging the operables on some of those faces in order to provide that access. Another strategy that we've been using is in integrating fan systems in each of the living spaces, which provides that sort of occupant controlled comfort criterion. So you can see on the left was actually some of the preliminary renderings and proposal, and you can see how it's changed minimally. There's still articulation, there's still a breakup of the massing, and the balconies are still very present. But you'll notice that we've really refined the building massing. I mentioned the thermal boundary and how pieces were actually shifted, and some of the areas were outside of our main building block. That created some challenges. So it was very early on, we were able to switch things around, especially down in below grade parkade, which had quite a few structural implications as well as mechanical implications. They had a number of mechanical and electrical rooms that were outside of the envelope. And so we actually were able to redistribute the layouts in the parkade to incorporate those into this overall massing. So keeping in mind that a concise massing or a concise thermal boundary is very important to simplifying the design process. I'm going to stray into some of the above grade and detailing that we did decide early on. One of the main things was to determine what was our typical wall system. This is a wood frame construction. There is concrete foundations sitting below grade, but there are 6 stories of wood frame. Now the cladding is a mixture of metal and fiber cement cladding. And in order to achieve the wall assembly levels and passive house performance on the wall, we had 8 inches of insulation. And so we did have to think about how to support that much insulation in the wall assembly. So early on, there was a conversation of, do we do a traditional split insulated wall assembly, or do we attempt to potentially increase that insulation value by doing a blown-in insulation, a double stud insulated wall? The double stud tends to be something that we see more frequently on 2-story, 3-story buildings. We're seeing split insulated wall assemblies primarily in see these higher mid-rise applications. But the key consideration is also sequencing and also supporting that cladding element. The double stud wall assembly actually provides that structure outboard to support the cladding. What we're doing with the split insulated wall is spanning 8 inches of insulation in order to support the cladding. So then the question becomes, what is that supporting mechanism? How does it affect the effective R value of the insulation? So there's a number of products or strategies out there that we've looked at. In particular, we started looking at Cascadia Clips originally, but due to actually the simplicity and the thermal performance of a long screw attachment, we've actually ended up with a long screw attachment on the project. We can still satisfy the thermal performance requirements, but also we are ensuring that our wood strapping that is encasing the insulation is actually being provided level, and it is actually a cost-effective measure as well. When we look at some of the typical transitions, some of the details that have changed from traditional rain screen assemblies is in particular through wall flashing. Through wall flashing tends to be an area which draws a lot of heat and heat loss in the building, because we're bypassing of our insulation levels. In this case, and you can see on the left here that the membrane is fully adhered to the wall. However, we do have our membrane spanning across a sloped cut top of the insulation, and that is actually then lapping over a metal flashing, which is providing the break in the cladding system. That through wall metal flashing, or no longer a through wall, but actually simply on the outer board of the cladding, is then restrained in place with the strapping. So this is a proven detail that we've seen, and we actually had unique opportunity to go to several view the mock-ups at the BCIT campus, where their ongoing research is to produce details that are improving the passive house performance. So in terms of passive house design process, one thing that we do differently as well is there's a lot more thermal analysis early on. So we are often detailing early, as well as verifying and validating psi values early. And that always gets refined throughout the design process. And at every milestone, we then have to verify that compliance in construction as well. Unique conditions that also are low performing aspects of the facade is the balcony connections. So there are a number of ways of connecting balconies to the facade. In this case, we found that the cantilevered wood LVL, or engineered lumber, it was actually quite efficient in terms of its thermal heat loss. And so we were not overly concerned with the values and psi values on the project, and we were able to actually accommodate those losses in the envelope with our insulation levels on the project. However, one key aspect of these penetrations is that we are creating a hole in the air barrier. And in that case, there needs to be a lot of close consideration of the penetration detailing. So one thing that we've done is actually done a mock-up of this condition and walk through with the contractor on how to perform this air sealing around the LVL cantilevered beams. This is important just to make sure that we have an understanding also from a cost perspective early on that there is a process to be maintained throughout construction. And in terms of glazing considerations, we do have currently triple glazed assemblies on the project, and they are recessed, and there are opportunities for over insulating the frame, which reduces the psi value at the header. We usually model all of the 4 sides of the glazing using the product data supplied by the manufacturer, which is a Passive House certified system. And it allows us to sort of create these accurate inputs for the PHP model, which drives our end goal principles and criteria. In this case, the project has a lot of windows, but they are all high performing. And we are still meeting our target for U-value assemblies and for the overall heat loss in the building. I think I will pass it over to Nikolay at this point to jump to, oh, sorry, I have one more slide, but I'll pass it over to Nikolay to talk about his project.
Right on. Alrighty, I'm sharing my screen. Can everybody see that?
Yep.
Okay, perfect. All right, so let's talk about Sobel Tower. It is a 19-story existing residential tower constructed in the 1960s. It used to be residential, and City of Hamilton has repurposed it to be a retirement facility. This is the completed project. I will show you later on what that looked like beforehand. But the consultant team was with ARA Architects, and City Housing Hamilton are the owners. Some photos and location topography of where this is located. This is in Hamilton, right on the waterfront, really close to it. This entire area is being redeveloped and gentrified. So this is also a series of passive house projects that City of Housing Hamilton is undertaking. So this is their first flagship project. The existing construction of this building is a double wide brick, glazed brick assembly with interior insulation and 2 inches of interior insulation and gypsum board. You can see these panels around the slab edges. Those are not insulated. Those are just aesthetic metal covers for the slab edges. So every slab, every floor you see here, that is a thermal bridge which completely bypasses the building envelope. So the first order of business, we had to cut that out. We had to take these out and insulate them. And how do we do that? Well, we insulated it from the exterior. We provided an Eaves system to insulate the building from the outside. One more consideration were these balconies. When doing passive house, thermal bridging is critical, and at no point in our energy model, the PHPP model, could we afford to maintain these balconies. Some design options were to insulate the balconies and make it a 4-season room. However, that option was not chosen by the client because that increases gross floor area, and there led to some further challenges. So we actually ended up cutting the balconies off completely. In lieu of that, we've provided Juliet balconies so that the residents can open those up to get some fresh air. Existing windows, aluminum, non-thermally broken. I believe there were single pane windows, so very, very old building. So we had 2 strategies going into this. We knew that we had to insulate this from the outside because that's the most effective way to maintain a continuous insulated system without thermal bridges. However, through some value engineering, we've ended up going with a 6-inch Eaves system on the outside and about 4 inches of semi-rigid insulation on the inside. That came out of a couple weeks of design process and communication with the client and our design team. Reason being is there was some code challenges. We were trying to do some pretty fancy stuff here with bad insulation, fire-rated gypsum panel, and then Eaves. mineral wool eaves. That turned out to be a nightmare of a process, and we did some modeling and we found out that this option will work for us as well. We just had to make some concessions at other areas of the building. One note on sustainability here as well, and the benefits of retrofitting an existing building versus new construction, is that we save a lot on the CO2. Like, we, at no point here did we need to pour concrete. So all those savings, like, we were able to use the existing structural system, reinforce it where necessary, but we didn't have to tear this building down and start from scratch. So no recycling, no new resources, which I think is a real benefit of retrofitting. And like I mentioned before, it's possible to retrofit an existing building to meet passive house standards. All right, moving on. During the construction phase, we started taking out finishes, and with most existing buildings, especially ones that are 70 or 50 years old, there's a lot of deterioration, hidden things that needed to be addressed. There were some mold issues, bed bugs, moisture leaks, structural considerations. The building was overall in decent shape, but a lot of work needed to be done to bring it up to current code standards. So our Overclad strategy is a 6-inch mineral wool Eaves Durock puck system. So what that means is we have applied a continuous air and water barrier, a cementitious air and water barrier on top of the glazed brick. Then we adhered both mechanically and just with adhesive the Durock puck system. So that's a work in progress. On the left-hand side there, you can see the tower 80% complete with all of the Eaves installed, and the Eaves space code being gradually done up near the top of the building. Some detail in here for considerations on inside corners and how that translates into PHPP. So this thermal bridge here, the small one we can see, is unavoidable, but it is something that we were able to do nevertheless. Moving on, when building a high performance building, you get into the challenges of using systems and products that we haven't used before because they're considered a bit more premium and regular contractors haven't used them in the past. One of the challenges with this system is this Eaves is a newer product, especially the size of it. And what we know now is that we will ask the manufacturer next time to pre-cut these on site. Bottom right-hand image is showing us a section view of a through wall flashing. You can see here that there is virtually no slope to this. And the reason for that is because the site installers on site were doing the cuts manually. That resulted in a lot of variation during the application process and a lot of time going up on the mass climber to retrofit the conditions. As you can see here as well, this is a fully Eaves system, so we're not utilizing any PVC or metal sheet or metal through wall flashings. We're relying on Eaves tape and the base coat of the Eaves system to flash out our water, any rainwater that might come into the system, the envelope. At the ground floor, we have a mechanical metal panel cladding system utilizing both Cascadia Clips. And I believe this is here 12 inches of semi-rigid mineral wool insulation as well. So overall, very strong, high-performing systems that tested and proved to be meeting our expectations. These photographs are showing the in-progress work of cutting out the balconies and what that detail looked like afterwards. So we provided a bypass cover, so to speak, where we insulated the slab edge and provided a Juliet balcony style window above and below the slab edges to allow us to get fresh air into these units. Window considerations. So also passive house windows provided by Cascadia. These windows are passive house certified, and they're fiberglass frames with insulation inside of it as well. Windows are triple glazed with low E coatings on 2 out of the 6 surfaces. Sorry, 3 low E coatings on 3 out of the 6 surfaces. Some considerations here as well. These windows are aligned with our thermal control plane. As you can see, insulation, then the window. However, what that means is we can't put the window on top of the curb, the existing curb. We had to provide an angle. This angle, we've modeled it in steel to make it metal. That did not work for us. It did not meet the thermal bridge requirements. So this is actually a fiberglass angle, which was designed by our engineers, and it proved acceptable. There were some considerations, which I'll mention in a bit, but the angle with fiberglass, we actually had to reinforce it further because we found that it was deflecting too much and the windows couldn't be installed properly. This line, the blue line, is the continuation of the air and water control layer between the window and the existing and the wall, essentially the cementitious coating. It's an interesting product, Tremco ETA membrane. It's a siliconized sheet product. It does not come with any adhesives. It's just a sheet product, a ribbed sheet, which is adhered on site with a sealant onto the wall and sealant onto the window. And I'll show you. This is what it looks like. This is the siliconized sheet product, ribbed, and this was installed on site at every single window. It turned out to be a fantastic product, by the way, because it reduced imperfections. Like it was great. I was really happy to see the work being done correctly. I see a lot on site that we use peel and stick membranes where there's a lot of fish melts, voids, and they just don't really work. So this product allowed us to maintain our quality control, make sure it was adhered continuously throughout. And it turned out great. These are the fiberglass frames, or sorry, angles that I mentioned before, installed at every window to hold it up. We have anchors at the top, also sealed at every fastener penetration. So we made that very airtight. Our windows on the project, by the way, the operable ones for units that didn't have Juliet balconies are tilt and turn. So they opened up both like an inside and as a casement as well. Some more photos of the ETF. This fiberglass angle, when we put the window on it on shims, it deflected. So there was a lot of deflection in this angle, which prevented the installers from putting the units together, the different frames. So if you look here, it's actually 3 separate pieces of glass, or glass frames, all stacked together. At the joints, there's a T mold that's sealed between the two and slid in. And at the bottom, there is this trim piece as well that slides from across all 3 units. And this was impossible to install until we beefed up that fiberglass angle. All right, and we've tested this building a couple times. We did base building air testing, where, like I mentioned, we got a value of 8 air changes per hour. Then throughout the project, we did 2 guarded floor tests, where during construction, we wanted to make sure that we were meeting the passive house targets per floor. So we got to the 4th floor, for example, we put in our isolation materials to make sure we prevent, for example, the values in the elevator shaft from affecting our test. So we've isolated and guarded the 4th floor, we've tested it, and we were happy with the values that we saw. We did that once more and continued on with the construction work. And at the end of the project, we did a whole building air test once again and found that we met the passive house requirement for air tightness. This is a good diagram showing the passive approach to each individual unit, and also a scale showing, for example, that what doesn't need any interaction with the unit owner to something that can be interacted. So we're going from the building envelope, which, you know, the unit owners don't need to touch that at all, to windows, for example, the Juliet balconies that they can open at their leisure to get some ventilation inside and fresh air. Solar shades, that again, if it's a hot day, you put the solar shades down and prevent any heat gain coming in. We got a fan, we got a lightly tempered air delivered through the centralized ventilation system. That's part of the whole building maintenance strategy. And a decentralized cooling boost through a variable air volume unit activated by the suite owners. So again, something that we can get a bit of air circulation and fresh air inside the suites. And lastly, this is a diagram showing the fresh air supply to each individual suite. with Passive House, because we have such a low value for air leakage, we don't get the fresh air we would from air leakage. So we actually need to make sure we supply the fresh air to each individual suite, and that needs to be part of the design process. So this is our strategy. We had a centralized a duct that delivered fresh air to each one of these individual units. And and the last slide here is just a summary of the 5 Passive House principles. And that's it. Any questions?
Thanks, both Timothy and Nikolay. Lots of information to digest for sure. And I hadn't mentioned it at the beginning of the session, but we do have some time, about 10 minutes right now for questions. So we can either you can either unmute yourself and just go ahead and ask the question out loud, or if you want to put it in the chat, I'd be happy to pass those along as well. Maybe just for starters, while everyone's typing away their questions or thinking about their questions they might want to ask, I thought it was so interesting that the work that you did with the contractor around ensuring the proper insulation or proper air sealing, rather it was. And I'm just curious what the outcome of that collaboration was, and was it successful?
Yes, it was successful. So PCL were the contract to do this work, and although they haven't utilized Passive House certified tradesmen, they themselves, the site supers, I believe, had taken some classes in Passive House to familiarize themselves with this process. So working with them, it was good, because they had an understanding of the level of performance that we're trying to achieve. So a lot of the times on site, I get people saying, "Oh, why are we doing it this way? I've done it this way for 30 years." And on this project, PCL actually got a bit more knowledge and helped us out with this, and they forced their contractors to do it this way. And it was great to work with. The window guys, we got lucky with them as well. We had a lot of good experiences on past projects, and we brought them in on this one as well. And it was a treat. We suffered a little bit with the Eaves guys, because I'm sorry, but their work was a little sloppy here, and this is where most of our time on site happened to be, resolving these deficiencies.
Yeah, it just goes to show the importance of kind of working with the trades. One of the things that we've been working on as well is how to really upskill the workforce in order to kind of apply these at scale, right? So how do we start applying some of these techniques at scale? So really important to kind of pursue that work with the contractor and the trades. So we do have a question here on the Ken Sobel building. Was the VAV ductwork already in place?
No, we had to install new ductwork. So elevators were modernized. At the same time, we got access to near the elevator shafts in the core, and we put a new ductwork in.
And then did you install any heat recovery equipment?
Yeah, so it's my understanding is that this number 5 is this cooling boost material. I can't speak too much to this. I'll be honest, I was doing the building envelope portions of it. We had a mechanical consulting team that took care of this portion of the work, but my understanding is that we had an air handling system with the roof, and each unit had this decentralized system.
Okay. And I have David, who is going to unmute himself and ask a question.
Hi guys, thanks for the presentation. I just had a question for Timothy, actually 2 questions. I'm just wondering what mechanical system you ended up using for cooling. I think you mentioned ground source, but I'm not sure if you selected that. And then also which products ended up, that you ended up using certified products for. Like I think you mentioned Windows, but were there other ones?
So for the mechanical question, I think the ground source was Nikolay. I think that was, you mentioned that. For us, we used the HRV units, similar system, decentralized system, for all of the heat recovery or heat exchange on each of the residential units. Is
So
that
there was no, but there must have been an actual mechanical heating and cooling system as well as your HRVs, right? Like,
yes, we did have a cooling system as well, out of request. Even though we did have passive strategies for overheating, we did want to have some active cooling measures incorporated. So we do have, yes, we do have the air tempering for heating and cooling provided on the building as well. But again, I think we're less on the envelope in that regards, and so we often work closely with the mechanical engineer on the project to make those decisions. But
okay, thanks. Yeah, sorry, I forgot that you're focusing mostly on envelopes. So
no worries.
Sorry for the curveball question.
And then the second part of the question was, what were the final glazing systems selected?
Well, no, I was just wondering about passive certified products. So I know you mentioned Windows, but were there any other products that you used that were passive house certified?
Yeah, so actually we are, so this project is currently just entering CDs, and we kept the passive house certified windows for all the residential openings. And that was the Innotech system as basis of design. But we ended up actually switching out the storefront or entry systems for a non-certified system. And that's because we could actually still meet our requirements even with the lower performing assemblies. So we're actually, I think in that case, we're using a typical Conair entry system.
Great, thanks.
Yeah, likewise for us as well. Each unit, residential unit, had the passive house certified windows, but the top floor solarium and the ground floor areas were non-passive house certified windows.
And another question on the, or a question on the Overclad, what was the additional cost per square foot compared to a traditional system?
Don't have that information available for right now. We have done this exercise, just don't have it in front of me. Tim, do you have any info?
On the Overclad?
Yeah.
Not. I know I've been requested to not share cost information at this point. So, but definitely something that we'll probably hope to provide as a later point in time. So,
yeah, I will say though that the Eaves system that we chose in the Sobel Tower was the most cost-effective approach. We were considering insulated metal panels, metal cladding. Then we ended up going with Eaves.
As a kind of an overarching, knowing that these were both kind of targeting that affordable living, was there a cost increase total that you were trying to work within, like what percentage, in order to meet the targets, but without going obviously way out of the budget of the affordable housing?
Yeah, I can't speak to that. Sorry, clients asked us not to disclose any of that kind of information.
No problem. Do we have any kind of final last minute questions or one last question? There's a question about what the overall peak load was reduced to. That would probably be on energy use, I'm imagining.
Yeah. We did achieve the 15 kilowatt hours per meter squared per year though. So we were able to get that down.
I see Vedran also has a question.
Hi, Pam. I raised my hand, but you probably didn't see it.
Sorry, Vedran, go ahead.
Yeah, no worries. No worries, Pam. Thank you, Nikolay and Timothy, for a wonderful presentation. I have one very detailed and one global question, general question. The detailed question on Timothy's slide, I believe it was somewhere around the 111, when you were showing that through wall flashing. I think I missed it. How exactly did you resolve it? Did you use the different type of material to figure out that through wall flashing, or?
Yeah, so the way we were able to do that was actually we did specify a higher density mineral wool insulation. So that is I believe the comfort board 110. The reason for that was both from the long screw attachment approach, but also to provide a better surface for cutting these sloped cuts in the insulation. In terms of the actual membrane, it is I believe we're currently holding a Sika type membrane. It's a self-adhered flashing, and what they can do is actually prime the top cut surface of the insulation so that there is a bond created between the membrane and the insulation. But that whole through wall flashing is no longer bypassing the insulation. The only sort of cut is made by the membrane, right? So we're drastically reducing that thermal bridge.
But this is a linear detail, right? This membrane goes linearly
all the way across
throughout the length, and so there's no metal to support that membrane.
No, it's
just membrane. So that's the trick. There's no metal, right?
Yep, it's fully supported by the higher density mineral wool, and then that surface is also because of the primer is also hardened, so it's just easier to bond to.
And
sorry, go ahead, Nikolay.
Yeah, one comment towards the metal is we needed through wall flashings at the window heads for Ken Sobel, and we actually used PVC through wall flashing for that to reduce the linear thermal transmittance. That's just another product option that we can consider.
We're a strong advocate against PVC, but that's okay. That's another story. And the more general question to both of you, I guess, is how do you deal with curtain walls? I noticed that projects that you're presenting have punched windows, and Cascadia is a proven product, but how do you deal with curtain walls?
So I think with curtain wall approaches, that's definitely less. At the moment, it's less frequent with passive house projects. I think largely due to the high glazing percentage, right? Now more and more systems are coming out with a curtain wall that has a higher amount of opaque assembly to it, or spandrel, right? And where we can actually increase insulation levels. So I don't think it's impossible.
It's definitely possible. It's just a cost consideration for curtain wall. Curtain wall is at the minimum 30% more expensive than a window wall system. So it definitely drives the costs up, but they're very versatile, and they can be designed to meet the passive house standards.
Fantastic. Well, thanks so much. That does put us slightly over time. I really appreciate the presentation and the time you took today, Timothy and Nikolay, to share the info about these two projects. I just want to let everyone know that we do have another event scheduled in November 17th, I believe it is, and a slight change on that one, or slight shift, is it'll be talking about net zero. So one of our projects that we're actually funding here in Edmonton. So please take a look at the website and get registered for that. Otherwise, thanks so much for joining us today, and we hope to see you again.
Thanks for having us.
No, thank you so much.
Thank you.